There are many ways to solve a quadratic equation. You can factor, you can use the quadratic formula, you could graph, and you could complete the square. Now, completing the square is not a favorite for a lot of students because it requires this arbitrary b over 2 squared, and where does that come from? Today I'm going to show you where that does come from, and I'm going to show you a lot of other things related to completing the square. So let's get straight into it. So why do we complete the square? Well, the point of it is to turn any quadratic equation into some form that's a modified perfect square. So we basically can multiply this by something and then add something else to it to make this equivalent to that, okay? So let's kind of just do that. So first let's look at what a perfect square foils to. So if you FOIL it out, this just becomes x squared plus 2dx plus d squared, okay? So that's pretty straightforward. I mean, nothing too significant there. So let's look at this, okay? We want to turn this into some sort of form like this, and we have an a out here, and that's kind of annoying because it's kind of messing with a lot of stuff, because, you know, if we had an a here, that would be helpful. So let's kind of just divide by a to make things easier. We could pretend a is just 1, but I mean, that's just too basic, and it's not going to give us like a general case. So let's just divide each term by a, and then multiply. We can like factor out an a basically. So I'll show you what I mean. So y equals, we have this lonely x squared, and I'm gonna have that a there, but I'm gonna factor it out, and I'm gonna have this plus b over a x plus c over a. And if you distribute this a to each of these terms, you're gonna keep getting this same expression. So you didn't change anything, you just factored an a out. Okay. Now, I'm going to do some substitutions just to make it clear where everything is, because at this point now your b value and your c value are different. They're now b over a and c over a. So I'm going to make it so that b over a is equal to capital B, and that c over a is equal to capital C, okay? And I'm going to show you, it'll make sense later why, but yeah, so now with this substitution, we have this a times x squared plus capital B x plus capital C, okay? Basically just, I did a substitution, nothing too special there. Okay, so now we can kind of notice that this looks very similar to that. We have our x squared term, we have our the coefficient in front of the x, which is there, and we have a constant. So because d squared is just a number, d could be like 5 or 4 or 7 or 20, you know. Another thing you might notice is if you actually multiply this by some, let's say r, you multiply that, you have an r multiplied by the whole thing. So that's pretty cool. So that's like another similarity there, and that's kind of like you're starting to probably gain the intuition like, oh, that makes sense. But we want to make sense of where the b over 2 squared comes from, because that's the point of this video. So let's just, so we already noticed that these two equations are pretty similar, that they have the same components, but not the same coefficients. Like the b and the c and the 2d and the d squared, they're pretty much coefficients and constants, I guess. So let's actually set up a system of equations to look at this better. So we're going to have this b is equal to 2d, okay? Bx is equal to 2dx, you can just divide by x, but that's not really significant here. So then c is equal to d squared. Okay, so now let's just solve for d, because this d up here is kind of just a general form, so let's actually see what we come up with. So we can divide by 2 on both sides, so b over 2 is equal to d, and then we also see here that the square root of c is equal to d. This is actually plus or minus, which is interesting. So that's actually very cool on itself, and I'm going to kind of stray off from the main point of this video for a few minutes here, because this is very interesting. We found that d is equal to b over 2 and square root of c, and this is cool because you can actually replace this d with those values. So let's say we have x plus, let's say x plus, yeah, okay. Let's come up with an example. X squared plus 4x plus 4. Okay. So that, if we factor it out, well, using these, we could actually very simply see that this is just x plus 4 over 2 squared, which is just equal to x plus 2 squared. Or we can also see that this is just x plus the square root of 4, because the square root of 4 is there, squared, and that's also equal to x plus 2 squared, okay? That's not x minus 2 squared, so there comes a little issue with that last one. But this is cool, because this is actually correct. You can actually FOIL these two, and you'll get x squared plus 4x plus 4. So that's a cool fact on its own. But you can notice that, well, look, we have b over 2 is equal to d, and we also have square root of c equal to d, so couldn't we set those equal to each other? And the answer is yes. Because look, so if we set b over 2 equal to c, we could first, square root of c, yeah. We could first see that, okay, well, we could say that b is equal to 2 times the square root of c, and I'm just keeping it positive for just simplicity. Okay, that's cool. But also, we could reverse this and say that c is equal to b over 2 squared. And that's where that comes from. Now, usually it would be the lowercase, but I have capital. The reason why is because we already divided by our a value. So typically what you do is you take your y, you take this expression, divide by a, and those new values are what you input into this. So that's why I have the capital there. Okay. So, this is interesting because this actually correlates a lot of things. So let's actually do a substitution into this equation. We get y is equal to our lowercase a times x squared plus, and we could write it as 2 root c. So let me do that first. 2 root c x plus c, okay? But, you know, with the plus and the minus, it's kind of just confusing. So that's why this is the standard form. Y equals a times, we could do x squared plus bx plus b over 2 squared. And so that forms a perfect square, okay? Now, which perfect square? Well, it's actually pretty simple because you can actually make the substitution back into here. Remember that d is equal to b over 2, so this is simply, I'm going to get rid of the r to get rid of confusion, but this is simply just x plus b over 2 squared. So this is equal to y equals a times x plus b over 2 squared. And that is your form. That's it. I mean, that's it. So now the problem here is we have this equation, but we're not always going to have the coincidence where this number is a half squared of this number. We're not always going to have that. Because if this is 4, then this would be 4 divided by 2, square that, so that's going to be 4 divided by 2 is 2, 2 squared is 4. It's not always going to be that. This could be 5, or it could be 200, you know? So the reason why is, let's say our c value is something else, and we want to put it in a perfect square, so we put it in this form, but we also have to get rid of we have to get rid of this number that we generated because we just came up with it out of nowhere. So we have to get rid of it. And then at the end we can add the original c value we had. So that's pretty much completing the square, why it works, and other cool little facts that people don't actually know. And I was actually very surprised when I was thinking about this stuff, because I realized, like, wow, this kind of stuff, like, they don't, in high school, teachers don't teach you this stuff. But it's interesting to come up with. So yeah, that's pretty much it. Thank you for watching, and I'll see you later. Bye, guys.